Hi-oh, here we are. Some basics on motion and definitions. We have our guy brought to you by Gary Larson in the cartoon The Far Side. He's sitting there stranded on some deserted island, and he gets a little hope in his eyes as he starts to see a ship. Hey, hey! Hey, save me! I'm over here! I'm over here! And it turns out to be a little boat. Well, it's a great way to begin the idea of things being relative. Here's a quick Malcolm in the Middle video. Check it out.
Life is unfair.
So you can shoot burritos better than me. Fine, whatever. Big deal. That's all you got in me. Can you stop a ceiling fan with your head? I didn't think so. And look at this. My popsicle's like twice the size of yours. What a score. I am totally Reese. Oh.
And another one, the video quality isn't all that great, but it gets the idea across. It's pretty good. Watch this.
How much energy? A large amount or just a little? It all depends on our point of view about the burning of a match. What we think we know depends on what we see. What we see depends on how we see. How we see depends on us. It depends on our point of view. We also know that appearances can be deceptive. For many things depend on our point of view. Whose egg is this? A hummingbird or an ostrich? This is a hen's egg. And we all know size is relative. Who's moving? Movement, too, is relative. It depends on your point of view. If you're on the bank, it looks as if the barge is moving and the man isn't. If you're on the barge, it's the other way around. We all know that. It depends on your point of view. At sunset, is the sun moving or is it the earth? It looks as if the sun is moving even though we know it's the earth rotating. After all, our point of view is almost always from the earth, and the earth usually seems pretty steady, even at sunset. But other things we feel we know, time, space, matter, energy, are not always what they seem in everyday life. Albert Einstein saw this.
Well, it turns out all motion is relative. Everything. And that's really what we want to focus on. Motion itself. Don't worry about time and everything else, but motion. You know, we have these two baseball players. Compared to the batter, you hit the ball is moving away from him at 30 meters per second. And one would probably say, well, it's coming towards the pitcher at 30 meters per second. However, we have to account for that person's motion as well, because not only is the ball coming at the pitcher at 30 meters per second, but the pitcher is coming towards the ball at 10. It's going to have a net effect as if that ball hits that pitcher's glove at 40 meters per second. So when we say things are relative, what we really are saying, it depends on the individual's point of view. We're measuring it with respect to some other object. We have Foxtrot here. Okay, here's the play. Go 40 yards downfield, then turn left and go 20 yards, then turn right and go 25 yards, and turn right again and go 30 yards, then turn right and go 30 yards. And you could keep reading this through, but the punchline is, well, I'll be right back where I started. And his response is, I can't throw very far. So what we're talking about is a displacement of 0. This guy went a huge distance, went 40 plus 20 plus 25 plus 30. Well, and that's the distance they ran, but started right back. And we call that displacement, where you end up from where you started. Couple definitions. Rate. Anything with respect to time. So in other words, we know miles per hour. That's our speed limits, right? That's a rate because we're talking about per time, per hour. Heartbeats per minute. That's the rate of someone's heart beating. Again, it's a rate. Anything with respect to time. The first rate we need to talk about is speed. And that's something you're familiar with. You drive down the road. You look at your speedometer. It tells you how fast you're going. In other words, the rate at which your position changes. If I am going 10, I'm going to start using meters. Meters, which is a distance, per second. Look at that. There's our formula. The distance you go divided by the time. It tells me every second I will have moved 10 meters. However, your speedometer tells you something called the instantaneous speeds. Tells you exactly how fast you're going at that moment in time. It doesn't tell you about the entire trip. For that, we need to talk about the average speed. If I start at home, let's say I'm going to run, here I am, my speed right now is 0. And then I start running. And maybe I end up with a speed of 3 meters per second. I wasn't going 3 meters per second the whole time. You can't say my average is 3 meters per second because I started at 0. I brought up my speed eventually to 3 meters per second. Instead, the average would be 1.5, right? 3 plus 0 divided by 2, since there's 2 measurements, it gives me 1.5. I had an instantaneous speed of 0 over here, an instantaneous of 3 meters per second over here, and various instantaneous speeds throughout. Be aware of the difference. Here's where it gets a little tricky. Velocity is just like speed, only you don't use it in your car. Your speedometer tells you speed. However, if your speedometer, let's say the needle is 0 right here, were to move this way, call it the positive direction, or it could move the other way, call it the negative direction, we can talk about the direction. We can go 10 meters per second to the right, or maybe we can go 10 meters per second to the left. That's velocity. Very simple. It's your speed with a given direction to it. Your speedometer doesn't tell you if you go north, south, east, west. It just tells you how fast you're moving. The last thing we need to talk about is acceleration. We're talking about rates, so we're talking about per time, and usually that means per second. The rate at which the velocity, so let's build this, so it's per second, the rate which the velocity changes. We're going to use a little Greek letter delta. It means change, and V to represent velocity. So it's the rate at which this changes. If you remember, in my example, I said, well, I start with a velocity of 0, and I end up with a velocity of 3. How did my velocity change? It went from 0 to 3, or a change of 3 meters per second. And if I did that in 1 second, then it would be change of velocity is 3, and I did that in 1 second, then my acceleration would be 3. We're going to have to develop the idea of acceleration a little more in class. This is a pretty tricky subject, but this is just the basics today. So how do you accelerate? Well, the key to think about is velocity. So if you want to accelerate, remember acceleration is a change in velocity, you need to change your velocity. In other words, maybe you're going 0 and you change it to 3. However, what is velocity? Velocity implies direction, right? That's the difference between velocity and speed. So if you want to change your velocity, not only can you change your speed, but you can change your direction. In my little picture to the side here, you can see this guy's turning the corner. Even though he may have his cruise control on and not changing his speed, he is changing his direction. He's accelerating. And that's what happens on roller coasters. You may not be going faster. In fact, you are probably going slower due to the friction. But suddenly, you twist and turn, and it feels like you're flying. Well, you are accelerating just because you're changing direction. Watch this. How about this one?